I'm Wes Skeffington. I'm with AMD, really legacy Xilinx, and so focus more on the embedded side. And today my talk's really just covering a bit of dynamic and multi-domain software and embedded devices. And really what I'm trying to get at is there's a number of projects and system considerations that we really want to continue to work with the open source community, work with Linaro on solving. And my role is that as a system architect. So I look at the hardware, software, and how we bring them together on our platforms. So agenda for today is really just to cover a little bit on the AMD embedded platform. So I just want to kind of define the context of the hardware targets that we're working towards, and how those link into the embedded applications. And the embedded applications, I've just got examples there on the right. And what's the common theme amongst those is the fact that we're dealing with heterogeneous compute and mixed criticality in all those systems. And so what I mean by mixed criticality, like in a robotics or even in automated driving scenarios, we're dealing with real-time systems and an aspect of non-real-time system being integrated in the same platform, and then being able to manage that and deploy software, firmware to both those environments on it. And then one of the things that's a key differentiator for AMD Xilinx and really any FPGA SoCs is this aspect of dynamic platform reconfiguration. I'll talk about a couple examples of that, but what that means is there are some tie-ins that we have from like the Linux community that we really need to work out. Platform boot firmware, I think that's self-explanatory. It's referring just core boot, being able to boot different OSs, different software. And then some of the work we want to do around secure world firmware and enhancing that. Today, for the most part, I would say our reference platforms show that there's something there. You can go do this, but we really don't tie that out because there are some gaps in being able to do that. Multi-domain software enablements, talking a little bit about why and how we're trying to do that with the open source community, and then just summary and next steps. But the key thing here is just this AMD plus Linaro. It's a key partnership. We really look forward to working with the community here to focus on these things that I'll call application agnostic system enablement. And this is where our mutual end customers really see value in what we do with Linaro. So a little bit on what AMD platforms I'm talking about, and I differentiate here just kind of just the level of maturity that we have to deliver in each of these platforms is a little bit different. So first is the Korea SOM. This we've heard several folks talk to. It's a reference platform for ARM. It's a reference platform for Linaro. And it's an ARM-based SoC. So really what you see here is this is the SOM. It's really basically an integrated computer module. It's got the DDR, the core SoC, non-volatile memory on that. And that is really intended to be a hardware platform that's production ready. That meaning that piece of hardware as is has gone through shake and vibe. It's gone through thermal shock. It's gone through all of those. So that piece of hardware can go as is into an end customer production system, into a, that robot example, or into a industrial controller, what have you. And then with that, we provide these evaluation kits where we take that SOM, plug it on to an example application carrier card where the application specific I/O is broken out, and that's an evaluation kit. Those kits we don't intend to go to into the end industrial controller. It's an evaluation platform for someone to get working. But that's often the target of our work with Linaro and the open source, because it's an inexpensive kit. You can basically grab it, plug it into the wall, and you're good to go with it. So it's a really important aspect for us and our partners in terms of building out those software stack references with it. We also have what we call evaluation boards. These are really critical for our chip down customers. So typically you think of AMD Xilinx, our primary business is selling a piece of silicon, a chip, and these are a method for customers to get to a broader set of our silicon and make use of that. And so we sell these evaluation boards, but you'll look at them, any hardware guy will tell you this is not a production ready card. This would not survive shake and vibe, but that's not its intent. Its intent is to sit on a desktop in a lab for someone to evaluate that and work to it, but also a place where This is where customers will first get our software references up and running and kick the tires with it, and then want to be able to take as much of that forward into their production systems, but not as is. That's one of the things to differentiate for AMD and these two platforms is our customers do not expect us to have a black box pre-built binary for them to take into their production systems. These platforms are a reference. I emphasize that because customers also are going to customize at these lower layers. So they need to take it, and I always describe it as Lego blocks that then they're going to snap together. So that's why open source is so important, is because they need to be able to grab that. They might use it 95% as is in our reference, but ultimately, like when they go to production, they're going to turn on Secure Boot. We have Secure Boot as a reference, but in these platforms, as soon as I burn basically our Secure Boot eFuse and tie it to their production keys, the platform becomes locked down. It's no longer really an evaluation platform at that stage. And then lastly, our newest platform is what we call Embedded Plus. This is really marrying the legacy Xilinx and the legacy AMD together, where we've got Xilinx Versal FPGA SoC with Ryzen. This is a platform you'll see out in the demo booth area where we're bringing together basically the x86 world and the ARM world. And this is a very common application use case in, for instance, industrial controls and robotics, keep coming back to those, where customers want to be able to have the horsepower of an x86, but the real-time capabilities of the FPGA SoC on it. So this is also a place, as we look at the software stack, what we can do in open source and continue to bring those things together. So for our embedded platforms, talking about the software solutions, really our goal is to let our customers focus on their application and market. One of the things that we see quite often is that, the customer is incredibly deep in, say, building an MRI system. That's where they make their product differentiation. Being able to boot Linux is just a necessary evil in their eyes. And so anything we can do as AMD and as partners in the open source community to make that, a low friction path, but giving them the appropriate capabilities is really necessary. And so that's why we focus so much on open source and coming up with the solution stack up to basically, I would say, to this area, because that's the necessary evil part of the stack. They know that has to be there, but they really want to focus on their user application piece of it. And again, providing that reference for them so that they can pull it in and make use of it. But we also are trying to use this as an example to demonstrate and educate our customers, because while that customer is an expert in building an MRI control system, they aren't necessarily following deeply all the good practices I should be doing from a security point of view down there. And so we often find that what we build out here as example and reference is also an awesome education tool for our customers to be like, oh, I hadn't thought about that. That's a really good thing, because if you just ask that MRI guy, do you care about security? The answer is yes, but they don't know what does that really mean? How do I translate into that? And so as open source community members, this is another opportunity for us to continue to use the great work that Linaro and the open source community is doing, is to put that in front of our mutual end customers who may not be following everything as closely as the folks at this conference do. So to talk a little bit about what's unique about some of the asks we have into Linaro is this dynamic platform configuration. And what this gets into is, if we look at, I think everybody's SoCs that is here at the conference has this ARM-based processing subsystem. In our case, we've got the heterogeneous A78s and the R52, so basically an APU and RPU cluster. But where we differentiate is we have this capability of basically FPGA fabric, programmable logic, that's in there. In more recent devices, we also have that AIE, so that's basically the ML accelerators. I think marketing's calling them NPUs now, but what have you. But the scenario is basically we want to be able to boot that processing subsystem, and then after that, deploy what I call a personality. So then I can figure out, okay, I'm an MRI application, I'm a robotics application, and then there would be different content that I load into that AIE or the programmable logic, and that's what we call a PDI, program device image, with it. But for the FPGA and AIE, we have customers that want to use those in different modes of operation. And the most sort of example that I think most people can relate to is we've got automotive customers that want to be able to have different content they load to AIE and PL based on the mode of operation of the vehicle. What that means is in park mode, I might have one FPGA image and a different AIE image. When I go into low speed mode, different images get loaded. And when I go into high speed mode, or basically highway mode, I have a different image that I get loaded into that. So when I do that, there's two things. Is dynamic load time is an important figure of merit for those customers. You can imagine that when you shift out of park and start to drive, you'd be upset if it took 2 seconds because I had to reboot the entire system, reload an entire new Linux device tree. That's just unacceptable. And so this is a place where, with the FPGA being actual programmable hardware, the ability to basically load device tree efficiently and unload it without issues is a critical ask and a critical figure of merit for FPGA SoCs. So this is not just an AMD Xilinx specific problem. This will also impact Altera, Lattice, and basically anybody that makes a programmable hardware SoC to it. So some of the things we're working with Linaro on is basically making sure we can cleanly unload that device tree. Loading generally works nicely. It's the unloading where you find your problems. And so some of the things we're working with Linaro kernel team is basically being able to do that unload. In particular, one of the problem systems is basically interrupt controllers. So typically we'll implement an interrupt controller in Fabric that then ties into the GIC of the PS subsystem. And so being able to remove that child node in the AXI is critical. Some of the other things that we also are working on is basically FPGA managers and upstream kernel driver for loading FPGA pieces. It's that's pretty stable, but in terms of basically bringing that into sort of the Linaro test Yocto images is something that we're discussing. And then we've got these user space libraries that we are AMD Xilinx specific, and those are open source, made available for customers to bake in to it. So this is an aspect of why that dynamic platform configuration is important. It has impacts, like I said, in terms of Linux kernel capabilities, Linux kernel configs, and just basically device tree overlay enablement in general upstream. So the capability is there, but upstream kernel does not enable it by default, and so that's something we're working with the team on. So talking a little bit about the platform firmware, what I'm really talking about here in boot firmwares is the core device boot firmware. So ignore security for a moment. I just want to be able to boot the device and do something useful with it. So in the last year or two, we've really been working with ARM and the Linaro team to basically migrate to SystemReady-DT. Now, unfortunately, when we launched Kriya basically a year before SystemReady spec came out. So what was really great to see is that our implementation is very closely aligned to what SystemReady became with it. So we can't quite get to a place where our legacy device, because we've got many fielded to migrate them to SystemReady, but working through that SystemReady certification to show to our customers that, like I said, that Lego block architecture, they can work to it. Future platforms out of the gate will be SystemReady aligned. So already covered on that. So the implementation of SystemReady you have to also take a look at, because there is an aspect of SystemReady. While the spec is there, there are aspects of device-specific implementation you need to concern. And so that's this image recovery and image selector are two things that we've open sourced relative to our implementation for the Xilinx specific aspects of SystemReady with that. And one of the things I call out why SystemReady, why the implementation of being open source is so important, especially for our devices, is just this example. This is a physical memory layout, which SystemReady needs to be aware of. In this case, this is a 1 gigabit NOR flash memory reference, but in our devices, our bank A, so in that AB update, With FPGA SoCs, the size of that image can vary greatly. So if I've got a 30,000 LUT or a 300,000 LUT FPGA SoC, the amount of memory I need to allocate and really the amount of NOR flash, so the size of the NOR flash device I have to buy, can vary greatly. So that's an aspect where having that open source as a reference, but then it becomes a trivial thing for our customer to go and tweak that based on whatever device they're using and its requirements to it. And then as we migrate to the full system ready out of the gate for the new platforms, again using FW update and LVFS, will really become our main way for doing these updates in the future. Today, we basically push the image to a package feed, the boot firmware image, and then we've got a little proprietary open source tool for actually doing and applying the update to it. But headed in that direction. Secure World firmware, really excited about what's happening here because today the reference platforms, like I said, we put out there, really we don't put out a secure OS example in those. And it's a place where customers, again, that point of education could really benefit. So we're really looking forward to some of the updates that are coming in TFA. We obviously use it today, but looking into the roadmap they have, one of those things that Minesh's presentation that was just the previous session, this slide's obviously dated because they released 1.0 like 2 days ago with it. But we're really excited about what transferless is going to bring in and that firmware handoff capability in terms of being able to build that Lego block example with the secure OS. And again, our system, so as a system architect, my motivations with this are really around device tree handoffs, being able to implement and start to stand up some of these hardware specific OPT secure services like the TPM, like the boot NOR flash and getting that off. With it, and then measured boot, which we already kind of have our own reference implementations, but it scales much better in this scenario, and it becomes a much more easily reusable block by our end customers with it. And what's here is basically AMD is releasing basically a new tool flow starting in later this month. That's called EDF. Embedded design framework, I think. Marketing's changed the name like 100 times, so but that's what it is now. But in that memory space and documentation, you'll see basically we're carving out already aspects for that TFA transfer list, TFA core runtime memory. So we're basically pre-allocating that so that customers can see that we have plans for it, working towards it. It's not there yet, but this is a lot of the work that we'll be doing with Linaro in the next 12 months. To it. Multi-domain software, this is the really last key piece. Another key point of Linaro partnership on this, as these SoCs are becoming more heterogeneous in hardware, correspondingly the software is also becoming more heterogeneous with it. And a very typical example I show here is on the A78 clusters, we might be running Zen, Linux might run an RTOS, QNX VxWorks, I don't know, next to it, and then the R52 clusters could be running Zephyr, a couple different bare metal applications. Very typical use case, especially in this Versal Gen 2 environment where we'll also have ISPs, number of ISPs running down here, and each of those need to have a corresponding real-time sort of accessory processor, if you will, helping serve them. And system device trees that the team has been working on, Stefano from AMD has been really helping drive it, but it's really been a devicetree.org collaboration with it. Really is key to making this simple for our customers to use so that when you create that flat hardware configuration, you can have a very simple and easy way for our customers to understand how do I translate and basically carve off what hardware this guy is supposed to have versus what hardware that guy's supposed to have. And in our devices, we also have an ability to basically do hardware enforcement of that segmentation. That hardware enforcement then is something that's typically customers really hard time understanding how to go configure that. And granted, it's complicated, but then they can start to tie that in. And it really just becomes a simple way for our customers to understand how do I go do this. And this is not an AMD specific problem, right? This is a problem for all the heterogeneous SoCs that are coming out. So, I'll just wrap with, we see and embrace, as a system architect, open source is key for several elements in that solution stack that we're talking about. SystemReady-DT boot firmware, we're really excited about continuing to collaborate and work on that, move that forward. Dynamic hardware configuration, again, there's a kernel aspect of that, of device tree overlays. There's a kernel aspect of being able to handle AXI interrupt controller, unloading cleanly with it. System device tree based domain workflow, that meaning that, a simple way for a customer to look at and leverage sort of the DT best practices we have in Linux, but then extending that to other OSs. Secure firmware extensions, so transfer list, the whole work around opt and refreshing on that. And so these are a few of the specific next steps towards, working towards that enablement for both AMD SoCs, but also just generally improving the overall open source and ability for our mutual end customers to, pull from that. So with that, thank you. Thanks for the opportunity. And, I'm blocking lunch. So any questions? Yeah, go ahead. Not that we need this, but.
Well, the dynamic aspects are really unique, I guess, to those type of platforms. So can you tell us a bit more how it works in practice when you switch from, for example, the car you mentioned driving slowly or on the highway? What happens at system level as seen from Linux?
Yeah, so what will happen is basically, so this FPGA, we have what we call CFI, so that's a configuration interface into it. And so what will happen is, so if I have image A, which is my park mode, and I've got image B, that's a firmware blob in the view of Linux to it. So what will happen is from user space, and again, we're talking about, we would ultimately want to run this all through Secure World in the future. But today, Linux will make a call down into FPGA Manager via our user space library. FPGA Manager will then indicate to there's actually this platform management controller is the gateway to that configuration, that something's coming, or that I'm going to reload the that same kernel library. Then at the same time, we'll make a device tree unload. So say I'm about to remove this hardware, remove the corresponding device tree. So we always load a bit stream and a DTBO. They're always married. And so when I make that call to load initially, I'm loading a DTBO and the bit stream. So then when I do an unload, I know disable and pull out the DTBO that I just had in there. And then via what we call the PLM, the new bit stream will get jammed in through that CFI interface. Once that completes, then that kernel side driver will then also load the DTBO with that bit stream. So that's kind of basically the orchestration that happens.
Wow.
Yeah.
And I think a while ago I saw a scenario where the live device tree of the running kernel was effectively amended as you described with a DTBO. So at this point, new drivers start to probe and be activated, right?
Yes.
Okay.
Yeah. So anything that's new, basically, when I load that, the DTBO has to be written and structured to match the PL design to it. But yeah, it's when that device tree is loaded that the corresponding drivers are actually loaded. And I guess the other thing is these are typically module type drivers. So then they only get probed at it. And that's why I say loading generally works well. It's unloading where any of the dependencies that a driver had throughout the system aren't always unloading cleanly. And so what we've had to do to date is a lot of testing, but you'll find out basically the device tree ordering can start to matter.
Okay.
Because, again, I'm not a kernel expert, but my understanding is, again, it's going to do a probe in the order that they're in the device tree, and then when they unload, they're going to do it in the reverse order.
Oh, okay.
So then you need to make sure that basically your dependencies are ordered properly.
Okay.
And those dependencies aren't always clear. which is why some of the kernel work is so important for us to get into it, because the kernel knows what those dependencies are.
Yeah.
They're just not always easy to discern out of your device tree.
Whoa.
Yeah.
Thanks.
Yeah. All right. Anything else?
How to make the switch smooth? Because maybe the low speed work mode have to maintain some calculation to keep the vehicle in a safe mode. When you switch to high speed mode, whether the status can be maintained.
Yeah, so that requires a lot of system level analysis. So you can basically view, realistically, the automotive use case I gave is that they're not reloading the entire fabric, they're loading a part of it. And
Okay, I
so
see.
we have a technology, well, all the FPGA guys have a technology to basically carve this up
I
through
see.
what we call a DFX. It's basically partial reconfiguration. So like the automotive example would be anything that's critical. Let's say like I've got my, let's say it's an EV, just to make it simple, that I've got my motor control for the system in FPGA fabric. So that part is always there.
Oh, I see.
Okay, and then I'll have a donut hole, a carve out in here of the aspects of the accelerator that are different between park mode, low speed mode and highway speed mode, and then just reload that part of it. Now, part of the reload process, we have what we call an IP that basically will, anything that goes in and out of that donut hole gets tied off appropriately and exits cleanly at a hardware level, so that you don't have to worry about like a bus getting stuck in a bad state. But there is an aspect to your point that the user architects their system of what goes into that static region versus the dynamic region in an intelligent way at a system level.
Okay, thank you.
Yeah. Okay. Well, thank you for this small group. Thanks for attending and appreciate the conversation. Take care.